Okay, so here's another example from Dr. Bob's notes to accompany the introduction to vibrations with applications. And we have a machine part that is 1.95 kilograms and it vibrates in a viscous medium. Ooh, interesting. So I think it kind of might look like this right here, right? So it's a little part. And here's a spring. And this is a little viscous medium right here. All right, determine the damping coefficient when a harmonic exciting force, which could also be, by the way, we could also be making some type of little thing right here, right? So it makes it go up and down. So you can picture that thing just falling back up and down. It's got a harmonic force to it, though. I guess I jumped it down here. P is equal to 24.46 newtons. Okay, so it didn't give us the thing. So just sine of omega f t right there. It results in, we'll call it a del. No, I usually go in x. Sorry, xm. I'm going to go xm is equal to 1.27 centimeters. And it's got a period. So we're not using damped period for these, by the way. It's kind of interesting. So this is going to be like a natural frequency period. So not the damped frequency. We don't do that for whatever reason when it comes to forced damping. So let's say we know this is going to be 0.0127 meters. Anything else? Oh, this is okay. So this is resonant amplitude. So R is equal to 1, if that helps us at all. We can get the period. We can get the natural frequency from this, right? So we go natural frequency is going to be equal to 2 pi over tau. That ends up being 31.42 radians per second, which you could do yourself. And we could also, with the natural frequency, I don't know if I need this, but I found it anyway, K over M, we could find that K is going to be equal to natural frequency squared times mass, and we happen to know both things, so we might as well find it. And 1.95, and so we end up with what? 1,925 newtons per meter. I'm not sure, I need this, but maybe I do. Well, it's a good thing to know. It's a good thing to know. I can go back into my relationship here. PO over K. Oh, I could, okay, so I can use that here. That's going to be 1 over the square root of 1 minus R squared plus 2 squiggle R squared. And I can plug all of these in. 0.0127, 24.46, 1,925, 1 over, and this is the resonant one, right? So that goes away. Maybe I should write that. I'll write it out anyway. Square root of 1 minus 1 squared. Doesn't matter, right? And then 2, and then we're squiggle times 1 squared. So we end up going in squiggle, ends up being 0.5003. Now if you go back to our graph right here, you can see that we could totally, we're going to be on 1 here. But you can kind of just like look at that and see already that we're close to being at 1. Look, that's interesting. At 1, we're close to being at 1 at the 0.5 squiggle. And so, we do know that the critical damping ratio is 2m omega n, which is 2 times 1.95 times 31.42, and that ends up equaling 122.5, and these are Newton second per meters. So C is squiggle times CC, or 0.5003 times 122.5 equals 61.3 Newton seconds per meter. And that was our goal here, was to determine the damping coefficient. Once again, like I mentioned in the previous examples, what we're attempting to do is to be investigators and find what the properties are of a system given a set of evidence. And so that could turn around in all kinds of different ways, mathematical tricks and that sort of thing. But it's what our goal is, so we'll go ahead and do it. I will see you in the next video.